Hello students, welcome to the second segment of our electrochem lecture. Okay, so as end off from the earlier segment, I will be talking about section 3 and 4 of topic 20 on electrochem. Yep, so if you have not gone through the first segment, please go and review the lectures via the link below. Right, so I will just jump straight into 3.1, which is the electrochemical cell. Yeah. So what is shown over here, which is the galvanic cell involving zinc and copper, is an example which we have used earlier on in sections 1 and 2. Yeah. So just to recall a little bit, zinc is the more reactive metal as compared to copper. So if we connect zinc and copper together in this particular circuit, you expect electrons to flow from zinc to copper. So you can view zinc as the electron donating source, but we don't use donating and withdrawing in electrochemical cell. Yeah, but just remember that the more reactive metal, it has a higher potential, so it will tend to donate electrons towards the less reactive metal. Yeah, so that means that at any one point in time, the more reactive metal will have electrons accumulating at zinc. So therefore, we will view this as the negative electrodes. Yeah, and then at the copper electrodes, electrons are being consumed by copper 2 because copper 2 will be reduced to copper. So we will, because electrons are being consumed, so it acts as like an electron sink. So at any one point in time, the copper electrode will be positive. Okay, and because zinc, in order to provide the copper electrodes with electrons, zinc will needs to be oxidized to zinc 2. So oxidation takes place. So this will be the anodes, and you would expect the electrodes to become smaller and smaller, and copper 2 will be reduced to copper 0 at the cathodes. So you expect the electrodes to become bigger and bigger. So this will be the cathodes. Yeah, of course, it will not increase forever. As long as the surface of the electrodes is more or less depleted, you would expect the reaction to kind of like stop. Okay, yeah. Yeah, so the wire connects the two electrodes together. We will need the salt bridge in order to maintain electrical neutrality. Yeah, so a lot of students don't really understand the term electrical neutrality, so perhaps I will explain a little bit over here. Okay, so just imagine that at the very beginning, right? Okay, which I'm going to write in pink. The concentration of copper 2 is equals to 1.00 moles per dm cube. Okay, and of course the concentration of sulfate as well, okay, is 1.00 moles per dm cube. So at the anodes is the same thing. So the concentration of zinc 2 plus will be 1.00 moles per dm cube, and the concentration of sulfates will also be 1.00 moles per dm cube. Okay, so now let me switch my pen to a green one. Okay, if you recall what happens earlier, what I mentioned earlier on, right? The zinc electrode will be oxidized so as to provide electrons, and the electron would push over to the copper electrode. Yeah, so when zinc gets oxidized, I would expect the concentration of the aqueous zinc 2 to increase. So it will increase beyond 1.00 moles per dm cube. And then over at the cathodes, I would expect the concentration of copper 2 to decrease, because now copper 2 gets reduced at the copper electrodes. So it will be lesser than 1.00 moles per dm cube. Yeah, and when this happens, right, you expect the solution at the anodes to become increasingly more positive. So it will become increasingly more positive. And then I would expect the solution at the cathode to become increasingly more negative. Yeah, because sulfate, remember, sulfate concentration remains fixed. Okay, if we don't have a salt bridge, that is lah. Okay, so my discussion here assumes that the salt bridge does not exist. Okay, now when you have an electrode becoming increasingly more positive, would you agree that now it is more difficult for zinc to be oxidized? Correct? Because now I have more and more positively charged zinc in the system. It becomes much harder for zinc to be oxidized to zinc 2. And the same case applies to the cathode. Yeah. So when the solution has less and less copper 2, then that means that the tendency for copper 2 to be reduced decreases. Yeah, so it will reach a point in time when there will be no more current flowing, because probably the system reached some form of equilibrium. So when that happens, this is not the situation we want. Yeah, so therefore the salt bridge is absolutely necessary, because the purpose of a salt bridge is for us to incorporate non-reactive or relatively stable cations and anions, in our case here potassium nitrate. Yeah, so that when my anode become increasingly more positive, then the nitrate will diffuse over. Yeah, so to make sure that the solution becomes sort of neutral. And when my cathode become increasingly more negative, my potassium will migrate over, so as to ensure that the solution remains more or less neutral. Yeah, so that is the purpose of the salt bridge. So later on there will be a little section which I explain to you, but I thought I just want to explain to you over here. Yeah, so most importantly, you need to ensure that the salt bridge contains a solution of non-reacting ions, in our case here potassium nitrate. It can be simply produced, okay, you actually do not need a U-tube. I think over here they mentioned that I need a U-tube. It can actually be created simply by cutting filter paper. You can just dip the filter paper into a non-reactive salt solution, and then you can just connect them over like this. It works perfectly fine. Okay, yeah, and I think over here I will need a high resistance voltmeter. I think it's already mentioned. Anyway, voltmeter must have high resistance, so the high resistance word may not be necessary, but anyway, just put it in. And then we also agreed earlier on that the voltmeter reading, the maximum value we can get is positive 1.10 volts at standard condition. And how do we calculate that, which I will show you later. I think earlier on I've showed you in the earlier lecture, but I'm going to show it to you again. Okay, so there are two reactions taking place. At the anode, zinc solid is oxidized to zinc 2, and the 2 electrons will then flow over to the cathode, where copper 2 will be reduced to copper. The overall redox equation is this. Yeah, and the flow of the electrons allow useful work to be done, so we can tap on the flow of the electrons to help us do the work. Okay, yeah, yeah. So oxidation half equation anode I have explained to you. Reduction half equation is the cathodes. Remember that cathode and anodes, the polarity is different for electrochemical and electrolytic cell. Yeah, but the processes is the same. So therefore, regardless of whether we are talking about electrochemical or electrolytic cell, anode is the electrode where oxidation takes place, cathode is the electrodes where reduction takes place. Yeah, but the polarity reverses. And I have explained to you the polarity of the anode and cathode being negative and positive respectively over at the electrochemical cell. So if you are still confused, please rewind back and take a look at the relevant sections. How does the salt bridge works? I have explained to you how it maintains electrical neutrality. Yeah, so you can read through this particular background information when necessary. Okay, I would like to give you a short introduction to cell notation, although this is not exactly needed in H2 curriculum, but it's good to know. Okay, so you notice that in the middle there is a double vertical lines. Okay, over here, so this double vertical line, so this is actually the salt bridge. Okay, yeah, then you have a single vertical line which represents phase boundary. Okay, so what is the meaning of phase boundary? Meaning between two phases. So if we have a zinc electrode, we'll just put zinc solid slash, and then after that zinc 2 aqueous. If we are using an inert electrode, let's say platinum, then there will be platinum solid and then slash, and then the 2 respective cations or any combination needed. Okay, so just be aware of this. So single vertical line, phase boundary, double vertical line, salt bridge. And it's often written from left to right. So the left hand side is the anode, the right hand side is the cathode. Yeah, so that is the convention. Yeah, so it's good for you to know. Yeah, so if the concentration are not written, then that you expect them to be in under standard condition. That is 1 mole per dm cube. And then for the purpose of gases, that will be 1 bar in terms of the partial pressure. Okay, yeah. So next, we're going to discuss 3.2 on standard cell potential. Okay, so you'll be worth to read this portion. If the two half cells are at standard condition, the cell potential we get is the standard cell potential. How do you represent standard? Make sure you remember to include the dots with a dashed line. Okay, so the cell potential is the potential difference between two half cell measured at standard conditions. Okay, which is 290 Kelvin 1 bar for gases, 1 mole per dm cubed for solutions. Okay, how can we calculate the standard cell potential? I think I've kind of shown you earlier on. Yeah, so I can just repeat over here. Yeah, so first we need to select the two relevant half cells. So go to your data booklet and select it. Okay, so I won't select for you because technically you can find the information yourself. That's why I mentioned earlier on that it will be good to use the E0 value in alphabetical order. So that it's easier for you to find. Okay, if it cannot be found, that means that it has to be given to you in the question. Yeah. Okay, so we have copper to copper and zinc to zinc. Yeah, so we write them down. We write it down side by side, and then the voltmeter reading will show 1.10 volts, which is equivalent to the standard cell potential. So that will be the difference between the two values. Okay, because each of these values is measured against SHE. Yeah, so please remember that each of these value is measured against SHE. Yeah, so in order to find out the potential, the actual potential difference, we have to take the difference between the two. Yeah, so eventually we will get 1.10 volts. Okay, if this is still a little bit confusing, maybe I can explain to you a little bit using a number line. I think that might be a little bit easier. Okay, yeah, so basically standard electrode potential, right, of the individual half cell, right, is measured against SHE. So SHE is taken to be 0 volts, so this is SHE. Yeah, so because it's measured against the standard, right, yeah, so if we move to the right, it will be positive, move to the left, it will be negative. Okay, yeah, so therefore when we look at copper to copper, what we are getting is 0.34 volts. Okay, and if we are looking at zinc to zinc, we are looking at negative 0.76 volts. Yeah, so this is with respect to SHE, which is taken to be 0. Yeah, so if the question is I have a battery involving these two, right, then what is the maximum potential it can generate? Then I guess it does make sense that it will be the difference between the two, which is between the reduction half cell minus the oxidation half cell. Yeah, so in that case we'll get 1.10 volts. Yeah, so this is the standard notation. E cell is E reduction minus E oxidation, or E cathode minus E anodes. Yeah, but I often will advise students, it will be good for you to simply write out the half cell directly involved. Yeah, so for the case of zinc to zinc and copper to copper, I will write it as E cell, okay, is equals to E reduction. Yeah, so therefore it's copper to copper standard minus E oxidation. Take note that although this is the E oxidation, right, but we will still write it as the reduction potential notation, so that it will be zinc to zinc. Okay, so please take note of this. Do not swap the sign over. It should be written as the reduction potential value, because this is how we define it. Okay, then this will be equals to 0.34 minus 0.76. Yeah, so we'll get positive 1.10 volts. Yeah, remember not to swap the sign, because whenever we want to take a difference, we must ensure that we are compare apples and apples, not apples and oranges. Yeah, so you cannot take an oxidation, you cannot take a reduction potential value minus an oxidation potential value. When we write it as E oxidation, we don't mean that it is an oxidation potential value. We mean that that is the half cell undergoing oxidation, but we'll still be using the reduction potential values. Okay, so I hope you're not too confused by this. Yeah, that's it. Okay, so zinc will be oxidized to zinc, copper 2 will be reduced to copper. Yeah, I think the rest are fine. Okay, so where the electrons are flow, I think I've already covered earlier on. So electrons flow from the oxidation half cell to the reduction half cell, so from anode to cathode. Yeah, I don't think this needs any more introduction. And we can use half equation to construct the Redox equation. So if you wish to, you can just write them out like that. Yeah, but for the actual reaction taking place, do take note that you are not supposed to use the half arrows. Okay, you must write out the actual process or the processes taking place. If it's oxidation, full arrow, zinc to zinc 2, reduction, copper 2 to copper. Remember that this is the actual reaction that is taking place. They are not at equilibrium. So you shouldn't be using equilibrium arrows at all. Okay, so I think this is the part which I need to emphasize. And the overall equation is this. So it only happens in one direction. If you want it to be in the reverse direction, then you need an external power source to drive the non-spontaneous process. Okay, then with that, let's look at exercise 3.1. Okay, so for exercise 3.1, we have this. The voltaic cell below consists of sulfate, sulfur dioxide, and then half cell connected to silver plus silver half cell. Calculate the standard cell potential. Okay, so again, what we can do is just to refer to the data booklets. Okay, yeah, but I can simply just write out E cell. Okay, so E cell, okay, is equals to E reduction minus E oxidation. Okay, so I think first let's look at the data booklets. We should find the sulfates. Let's try to find it. Okay, so this is the sulfate SO2. Yeah, so remember we need to look at the species present. So this is 0.17 volts. Okay, then silver plus silver is 0.80 volts. Okay, yeah, so in that case, in case you're wondering, is silver plus reduced or is sulfate being reduced? Okay, silver plus silver's reduction potential value is more positive than that of sulfate SO2. Remember earlier on, sulfate SO2's value is 0.17 volts. Yeah, so therefore sulfur will have a greater tendency to be oxidized to sulfates. Okay, so in that case, I'm going to expect E reduction, which is silver plus silver, okay, minus E oxidation, yeah, which is sulfates, okay, SO2. Okay, and then if you recall the earlier value, that will be 0.80 minus 0.17. Okay, so eventually I will get plus 0.63 volts. Yep, so this will be the answer for parts A. Okay, some of you might be asking why not E sulfates slash SO2 to E silver plus silver. If you do that, you notice that you get a negative cell potential. That means that the reaction is not thermodynamically feasible. Okay, yeah, so for part B, indicate on the indicates on the diagram the polarity of the electrodes and the direction the electron flows. Yeah, so you will know that for the electrodes on the right involving silver and silver plus, that will be the half cell where reduction takes place. Okay, so we know that when reduction takes place, this will be the cathodes. Okay, so let me write out this is the cathodes. And then on the left, sulfur dioxide is oxidized to sulfate, so this will be the anodes. Yeah, so electrons always flow from anodes, which is at a high potential, to the cathodes. Yeah, so in that case, silver plus will then be reduced to silver. And the anode is always the electrode where electrons accumulates. Okay, so therefore this will be the negative electrodes, and cathode is always the electrode where electron is deficient. Okay, they are electron deficiency because they are being used up in the reduction process. So this will be the positive electrodes. And then write half equations for the reaction that occurs at the cathode and at the anode respectively. Okay, so what's going to happen at the cathode will simply be silver plus aqueous plus electrons, and it gets reduced to silver solids. And what happens at the anodes will be sulfur, okay, aqueous plus H2O, and then it gets oxidized to sulfates plus 4H plus 2 electrons. We are not asked to write out the overall balance equation. We're just asked to write out the half equations. So this will be suffice. Okay, yeah, and sorry, the next portion is section 3.3 on standard cell potential and Gibbs free energy. Yeah, remember earlier on that I sort of mentioned that the standard cell potential is a thermodynamic variable. So definitely it must be linked to Gibbs free energy. We're not going to derive this, yeah, because the derivation you need some fundamental concept in physical chem. Yeah, so we're just going to showcase to you that the relationship between Gibbs free energy and cell potential is given to be this: delta G naught is equals to minus NFE. Delta G is the Gibbs free energy in joules per mole. Do take note that Gibbs free energy tends to be given in kilojoules per mole. So if you want to use this particular expression, you need to convert the delta G to joules per mole. Okay, and N is the number of moles of electron being transferred per mole of the equation. And F is the Faraday constant. The Faraday constant, as mentioned earlier on, is given in your data booklets, 96,500 coulombs per mole. Okay, so a spontaneous redox reaction will take place if delta G is less than 0, and this actually implies that the E cell is greater than 0. Yeah, so therefore, whenever we calculate the E cell between two redox reactions, or rather what the redox equations we are discussing, for example, if we are going to introduce SO2 into the system, and then with silver plus, we want to check whether there's a reaction taking place, we will simply be calculating the E cell. And then if we get a positive E cell, we will know that the spontaneous redox reaction occurs. And therefore, E cell taking on a positive value is actually linked to delta G, which takes on a negative Gibbs free energy. Okay, that has been discussed in the chapter on in energetics, which we discussed about a year ago. Yeah, and then to predict the spontaneity of a redox equation, if E cell is positive, reaction is likely to be spontaneous under standard condition, negative non-spontaneous. If E cell is 0, so the system is at equilibrium. Yeah, so there's no net reaction at either direction. Yeah, if you are a little bit confused, why is it that so does it mean that when a battery operates, the system is not at equilibrium? So the answer is yes, the system is not equilibrium. That's why the electron can flow. And then that's how your battery operates. And then once your battery dies out, which means the system is at equilibrium, no net reaction, no electron flow, what do I need to do? You need to recharge the battery again. Okay, yeah. Okay, over here you need to calculate E cell. This depends on the reactants given to you. These are some details given to you. You can read through. I will not attempt to explain, but I think giving you examples, going through the examples with you will make it a lot clearer. Okay, so for example, if I place a piece of zinc into copper 2, I do expect a reaction to take place. Because if I calculate the E cell, it's a positive value. Okay, but if I put a piece of copper into zinc 2, the E cell is going to be a negative value. Okay, why is that the case? Yeah, because over here the E reduction is now zinc 2 to zinc 2 to zinc, and then the E oxidation is copper to copper 2. So if I'm going to calculate the E cell for this particular process, it will be negative 0.76 minus 0.34. So I'm going to get negative 1.10 volts. Yeah, so therefore I don't expect the forward reaction involving zinc and copper 2 to take place. Okay, I think it's calculated for you here. Yeah. I can pause here for a while because if you have any issues, you might want to just rewind the videos a little bit and go through the earlier sections again. Because this is often the time when students have issues predicting E cell. Yeah, so they tend to often calculate a positive E cell because they do not take note of the reactants given to them. Yeah, and this can be quite dangerous. Okay, so for example, students might just calculate a positive E cell between zinc and copper by simply just involving themselves with the reaction involving just zinc and copper 2. But if they are given copper solid and zinc 2, they will still use this particular notation and calculation because the reasoning given is often I must get a positive values, right? But it does not happen that way. You must look at the reactant given to you in order to make an informed calculation. Okay, so this is something I need to stress to everyone listening to the lectures. Okay, so if you are confused by what I'm saying, let us look at exercise 3.2. I think it will be a lot clearer. Okay, yeah. So for exercise 3.2, we are supposed to predict whether the following pairs of reagents are likely to react when mixed in acidified aqueous solution. Calculate the E cell. Write a balanced equation for each case. Okay, first we'll look at parts A, where we have aqueous iodine reacting with chromium 3. We will first go to the data booklets to look at all the half equations related to the relevant species. Of course, after you become more experienced, then you will sort of have a memory, working memory on some of the likely reactions that you will use. But at this particular stage, I think it's easier if you can just look at what you have in your data booklets and then jot them down. Okay, so we have iodine being reduced to iodides. You notice that you do not have any iodine containing oxidized species in the half equations, meaning like you don't have IO minus, IO2 minus, IO3 minus, etc. Okay, it doesn't mean that they don't exist. They do exist, but it is not available in your data booklet. Yeah, since it's not available, you don't really need to worry about them. So there's just one equation you can write, which is the one involving iodine to iodide. Okay, so with that, I will write it down first. So I2 plus 2 electrons equilibrates to give 2 I minus, and this is plus 0.54 volts. Okay, and then after that, I'm going to look for the one involving chromium. Okay, then you notice that the one involving chromium 3, there are several equations which you can choose from. Okay, so I'm just going to highlight for you to take a look. So you have chromium 3 over here and here. So the first one is reduced to chromium 0, which is chromium metal. The second one is reduced to chromium 2, and then the next one is where chromium 3 is being oxidized to dichromates. Yeah, so for simplicity, we'll just write all the three equations, although off the top of my head, I know that I don't have to write all the three in. Yeah, but I'll just write all the three for simplicity. Okay, so I'm going to use a different color. Okay, so I'm going to have chromium 3 plus 3 electrons to give me chromium metal. This will be minus 0.74 volts. Okay, I'm just going to write it down. And then I have the chromium 3 plus electrons to give me chromium 2 plus. This would be negative 0.41 volts, negative 0.41 volts. Okay, and then I have the dichromate one, which is over here, and then it's 1.33 volts, so dichromate plus 14H plus 6 electrons. I'm going to get Cr3 plus 2 of it plus 7H2O. Okay, and then what I'm going to do now is I'm just going to highlight the main species involved over here. Okay, so you need to ensure that one is on the left and one is on the right, which I'm going to elaborate a little bit to you later on. Okay, so we have iodine. Okay, so iodine has only one equation, so I'm just going to highlight in yellow. And then next, you notice that I have chromium 3. Two of it is on the left, and then the other one is on the right. Okay, now you just need to ask yourself one question. Because I only have one equation involving iodine, so therefore for this particular reaction, iodine can only be reduced to iodide, correct? Yeah, so if iodine is being reduced to iodide, that means that chromium 3 must be oxidized to dichromate if I'm going to consider any possible reaction which this particular system can undergo, if you get what I'm trying to say. Yeah, so the reason why this is the only thing I can choose from is because I think number one, there isn't any other species which involving iodine which I can choose from. So let's say let's say just a random example, if I have like IO3 minus, for example, gets reduced to say let's say iodine. Yeah, then because for that example I have iodine on the right hand side, so potentially I can also try to calculate and see if chromium 3 can potentially be the oxidizing agent to oxidize iodine to maybe IO minus or IO2 minus or IO3 minus. Yeah, then I have a few equations to choose from, and I can calculate from there. But in our case here, because I only have the iodine iodide half equations, and that's the only one I have in my data booklet because I'm limited by what I can do from the data booklet. Yeah, so the only equation I can choose is this. And if I'm going to choose this particular equation, then iodine can only behave as the oxidizing agent. So therefore, chromium 3 must be the one being oxidized, and chromium 3 must be the reducing agent. Okay, yeah, so but in our case here, I can only compare between this and this. Yeah, so if I'm going to calculate the E cell, okay, E cell which involve E reduction minus E oxidation, so which species is being reduced? Iodine is being reduced to iodide, so I'm going to write E iodine iodide I to I minus, okay, minus of E dichromate, okay, and then chromium 3. Okay, so you notice that if I'm just going to punch the calculator, I'm going to have 0.54 minus 1.33. Okay, I forgot to write, this is actually 1.33 volts. Okay, so I'm going to end up with a negative value, so that will be negative 0.79 volts. Okay, so because it's negative, I do not expect the reaction to be spontaneous, so my conclusion will be no reaction will take place. So because of that, I do not need to write a balance equation because no reaction is going to take place. Okay, so that's all for part A. If you still have any doubts, I think it will be good for you to continue working on the remaining parts and then try to attempt some of the questions in the tutorial. Because for electrochem, especially the very beginning parts when we are asking you whether a reaction is likely to be spontaneous or not spontaneous, I think a little bit of practice does make a lot of difference. Okay, so I'll really urge all of you guys to practice as much as you can. Yep, okay, so for part B, again, it's the same thing. We have H2O2. I think earlier on we mentioned that H2O2 can behave both as an oxidizing and reducing agent. Yeah, but now you are a little bit clear on how to choose equation in a strategic manner. So therefore, I'm just going to jumpstart and look at the other reagents present. So the other reagent present is permanganate. Yeah, so I'm going to scroll down and look at permanganate. Okay, so permanganate, there are a few equations involved, but as you know that we are performing the reaction in acidic medium. I think it's over here, acidic medium. So assuming that is excess acids present, so I'm only going to choose the one involving excess acid, which is permanganate reduced to Mn2+, okay, which is 0.54 volts. Okay, so in this case, I'm just going to draw a line across. Okay, so I'm going to, over here, I'm going to choose permanganate, okay, reduced to Mn2+, and then plus 4H2O, and then this is 1.52 volts. Okay, and this is the only equation available, so therefore permanganate is behaving as the oxidizing agent. If permanganate is behaving as the oxidizing agent, that means that H2O2 is behaving as a reducing agent. Yeah, so if I'm going to choose my equations, I need to choose H2O2 to be on the right hand side, because if H2O2 is behaving as a reducing agent, itself will oxidize to oxygen. Yeah, so I'm just going to compare this, okay, which is 0.68 volts. Okay, so I'm just going to write it down. So O2 plus 2H plus 2 electrons, I'm going to get H2O2, and then this is 0.68 volts. Okay, I'm going to highlight the important species. So permanganate is the oxidizing agent, H2O2 is the reducing agent. So I'm going to calculate E cell. So E cell in this case is E reduction, which is permanganate Mn2 plus minus E oxidation. In our case here is oxygen H2O2. Yeah, so I'm going to end up with 1.52 minus 0.68. Okay, I'm going to end up with a positive value. So this is going to be 0.84 volts. Okay, and since this is a positive value, I will conclude that the reaction is spontaneous. Okay, so reaction is spontaneous. Reaction is spontaneous. And then I would expect effervescence of oxygen gas to be given off, because this is oxygen gas. Okay, and then permanganate will be reduced to Mn2 plus, so therefore purple permanganates will decolorize. Yeah, so as per all redox processes, I'm just going to write a balance equation. So MnO4 minus 2 of it plus 6H plus 5H2O2. Full arrow, I'm going to get Mn2 plus 2 of it plus 8H2O plus 5O2. Okay, yeah, so this is how we go about working on the problem. Some of you might be wondering, why didn't I choose the one involving H2O2 on the left hand side? Yeah, but as I mentioned, if H2O2 is on the left hand side, it is behaving as an oxidizing agent. Yeah, but right now, because we are using permanganate, and there's only one equation involving permanganate from left to right, so therefore H2O2, I must choose the equation involving it as an reducing agent. Yeah, so that will make sense when we calculate E cell. Basically, you can't have the two species on the same side, because that will not make any sense at all. You can't have an oxidizing agent reacting with an oxidizing agent. Both can't be reduced together. Yeah, but if a more powerful oxidizing agent is potentially possible, it is possible for it to potentially oxidize a weaker oxidizing agent, provided you have the relevant data. If you do not have the data, then there is no point in any further discussion. Okay, yeah. Then next, I'm going to move on to part C. Okay, so for part C, we have vanadium 3 plus and copper 2 plus. So we'll go to the data booklets and check out the equation involving vanadium 3 plus. In fact, so for vanadium 3 plus, we have two potential equations. So one, we have vanadium 3 on the left, another one we have vanadium 3 on the right. So we're just going to copy these two equations in here. So we have vanadium 3 plus, just need to make sure it's sharper, vanadium 3 plus plus electrons. I'm going to get vanadium 2 plus. This is negative 0.26 volts. And then I have vanadium 4 plus 2H plus electrons. I'm going to end up with vanadium 3 plus H2O. Okay, so this is 0.34 volts. Okay, and then for copper 2, just going to go back here. Okay, so for copper 2, we have copper 2 to copper, and then copper 2 to copper 1. Okay, so I'm just going to write both down, and then just going to use a different color. So from copper 2 to copper, okay, so that's to copper, this is plus 0.34 volts, and then copper 2 to copper 1, and this is 0.15 volts plus 0.15 volts. You'll notice that I do not have an equation involving, say, copper 3, copper of a high oxidation state, to copper 2. So which means we don't have one where copper 2 is on the right hand side. So therefore, if I'm going to highlight, I have vanadium 3 here as the oxidizing agents. Yeah, and then I have vanadium 3 here as the reducing agents. And then for our case for copper, both copper will behave as an oxidizing agent because they themselves get reduced. Okay, so if I'm going to check out which two are potential reactions, which are the two pairs, so that will be the one involving vanadium 4 to vanadium 3. Okay, then with either of the two. Okay, so either this with this or this with this. Yeah, but you notice that either case, when we try to calculate E cell, so let's try to calculate E cell, the one involving vanadium 4. Okay, so E vanadium 4, so we have vanadium 4 to vanadium 3 minus E oxidation. Okay, so the one involving copper 2, E reduction. Oh, sorry, I swapped the thing. Okay, so E reduction here will be copper 2 being reduced. Okay, so that will be E copper 2 copper minus E vanadium 4 vanadium 3. You notice that I'm going to end up with 0 volts, 0.34, and that's 0 volts. And because it's 0 volts, there is no net equation, or rather no net reaction, because an equilibrium is being established. Yeah, remember that when E cell is 0, right, that means that neither side is preferred and electrons will not have a tendency to flow from one party to the other. And I think this is understandable. So because we are getting a system at equilibrium, so therefore I do not expect any net reaction to take place. So they will probably just mix together and stay in that state. Okay, so I won't even write out a balance equation in that sense. Yeah, and then the next thing I'm going to deal with is part D. We have fluorine, the strongest oxidizing agent known to mankind. Okay, so I think I have stressed this quite a few times. So fluorine is over here. This is the strongest oxidizing agent known to mankind. And we have dichromates. Dichromate is something we saw earlier on. I think it's over here. This is dichromate. Yeah, but remember that because we have the strongest oxidizing agent known to mankind, potentially dichromate, taking on a +6 oxidation state, it could potentially reach a higher oxidation state, although this is likely to be a very unstable chromium species. Okay, but the issue here is that we do not have the relevant data. So we do not have a data involving chromium at an even higher oxidation state than +6 being reduced to, let's say, chromium 6, in this case dichromate. So because we don't have the data, and in a sense here both dichromate and fluorine, they are written on the left hand side, so there is no way we can perform any calculation. Yeah, so therefore the conclusion for part D will be no reaction will occur because both of these are strong oxidizing agents, so no reaction occurs. Yeah, but always remember that when we conclude that no reaction is taking place, right, the conclusion is based on the available data we have, which is from the data booklet and whatever data they give us. Yeah, but if you are going to search up the internet for relevant information and you might find out more data, then you could actually propose more reactions. But remember, in the exam, in the realm of the exam, right, you are limited by whatever information is being presented to you. Yeah, so just work with whatever you have. I think that should be fine. Yeah, okay. So next, we are going to move on to the next portion, 3.4.1, related to non-standard condition. Okay, so remember that earlier on, all our calculation is based on the standard condition of number 1, 298 Kelvin, number 2, 1 mole per dm cube of the relevant aqueous ions in water, and then number 3, if it involves gaseous reactants, then it will be they will be introduced at 1 bar in partial pressure. Yeah, but in the course of reaction, many things can happen. For example, change in concentration, pressure, and temperature. So they can affect the electrode potential. So we can sort of predict these changes by looking at Le Chatelier's principle. I think it is not too difficult to apply Le Chatelier's principle in this sense, because you would have reviewed that when you are revising for your lecture tests for acid-base equilibrium, the consolidation test you have just taken. Yeah, so if this is a major issue, then I will urge you to review some of the concepts you have learned from acid-base equilibrium and chemical equilibrium last year. Yeah, so one of the tips which I will propose to students usually involve revising electrochem together with chemical equilibrium and acid-base equilibrium because they come as a package. Okay, yeah, so let us look at some examples. So effects of concentration of aqueous ions on electrode potential. Okay, so remember that this when it's given to be plus 0.34 volts, yeah, this is assuming that I have 1 mole per dm cube of copper 2. If I reduce the concentration to 0.1 moles per dm cube, yeah, so I would expect the position of equilibrium to lie a little bit more to the left. Yeah, and because it lies a little bit more to the left, the reduction, the standard electrode potential will become less positive. So it will be less than 0.34 volts. Yeah, so in our case here, it will become 0.31 volts. This value is obviously taken from somewhere. Yeah, at the H2 level, you do not need to know how to calculate it because unless the equation is being given to you. Okay, then next, in terms of partial pressure. Yeah, so if we increase the pressure of gaseous species, yeah, from say 1 bar to 1.5 bar, I'm going to expect the position of equilibrium to lie to the right or to shift to the right, and therefore the standard electrode potential will become more positive. Yeah, generally we will avoid using the word less negative if, let's say, the reduction potential is a positive value. I think it will make the discussion clearer. Okay, and for the effect of temperature, let's say we increase the temperature from say 298 Kelvin to 398 Kelvin. There will be some slight change in the standard electrode potential value. Okay, yeah, so this actually implies that as the temperature increase, it actually favors the oxidation for sodium plus. Okay, yeah, and the next portion is Nernst equation, which is definitely not in your syllabus. Okay, but sometimes it can be given to you for you to perform some calculation for non-standard condition. Yeah, so the Nernst equation is given like this. So the E cell is equals to okay, this E cell refers to the E cell at non-standard condition. Okay, as opposed to the one with the dots above. The one with the dot above refers to the one under standard condition, and then minus RT over NF ln Q. If you're wondering how is there a way for us to derive this equation? Yeah, it can be derived quite easily. Yeah, I can do a short derivation for you in case for those of you who are interested. Okay, so we are all aware that at equilibrium condition, delta G, okay, is equals to minus RT ln K. Okay, so we are aware of this equation involving equilibrium constant and delta G. Okay, and of course, we are also aware that under non-standard condition, right, delta G is equals to delta G naught plus RT ln Q. Yeah, so this is at non-equilibrium condition. Yeah, why is it a Q? Because Q is the reaction quotient when the system is not at equilibrium. Yeah, so when the system is at equilibrium, delta G is equals to 0. So therefore, delta G naught is equals to minus RT ln Q. Yeah, so this is what you have learned in the topic on chemical equilibrium as well as energetics. Okay, so if you need to, please reference back to the relevant videos on chemical equilibrium or energetics. Okay, and from the above, we understand that delta G naught is equals to minus NFE cell. Okay, so if delta G naught is equals to minus NFE cell, so therefore delta G is also equals to minus NFE cell at the non-standard condition. Okay, and this is equals to minus NFE cell under standard condition plus RT ln Q. Okay, and I think from here it will be quite obvious because you can see that therefore E cell, okay, is equals to E naught cell if we divide by minus NF throughout minus RT over NF ln Q. Okay, so this is how this particular expression is being derived. So if you are interested, you can read up a little bit more. If not, it can be done by simple mathematics. Okay, and then we were also told that at 298 Kelvin, the Nernst equation can be rewritten in the logarithm form in this particular manner. Okay, you might be a little bit surprised, but again, it is not too difficult to write this out in this manner. So again, I'm just going to use some simple mathematics to derive it for you. Okay, the first thing we need to do is to dissect this particular term, which is ln Q. Okay, so when we dissect this term, right, what we need to do is first we can let y be equals to ln Q. And you know that ln essentially is logarithm to the base e. Okay, so that's natural log. Okay, so if I'm rewriting this, natural log Q. Okay, and what's going to happen here is that therefore from here, right, e to the power of y, okay, is equals to Q. Okay, and then I'm going to take log base 10 on both sides. So I'm going to have log base 10 ey is equals to log base 10 Q. Okay, and I'm going to shift y down. Okay, because you know that from mathematics, anything to the power, if you log it, and then you can just shift the power down. So I'm going to have y is equals to log base 10 Q divided by log base 10 of the natural e, or the exponential, I don't know what is it called, forgot what is it called, e. Yeah, it's the 2.78 something, that number. Okay, then from here, you can punch your calculator and determine what this particular value is. Okay, I'm sure you can do that quite easily. And then I think you will end up with about 2.30259 whatsoever. Okay, so what's going to happen here is that if you notice, right, y is actually log to the base natural log e and q, and this is thus equals to log 10 q over log 10e. Okay, so you notice that this is equals to this. So I'm going to equate this term with this, as well as to put in the condition, which is 298 Kelvin. Okay, and then R is 8.31 and F is Faraday constant. Okay, so what's going to happen here is that this whole thing will thus become minus 8. I'm talking about this portion. 8.31 times 298 divided by n, 96500 multiplied by log base 10 q over log 10e. Okay, so if you punch your calculator, this whole expression, if you don't believe you can punch it, is actually equals to 0.0591. Yeah. Why do we need to go through all the trouble? Because this is the easier form for us to calculate certain things using log base 10. Yeah, but you actually do not need to do all this derivation. When it's needed, then you'll be asked to do, or rather, it will be given to you. I'm sorry, you'll be given to you. You won't be asked to do. Okay, yeah. So I'm just showing you to so-called prove to you that the mathematics you have learned for the past few years, it will come in handy sometimes. All right, yeah. I'm gonna move on to the next section. Enough of mathematics. Okay. 3.4.2 limitation of using standard cell potential. Yeah, so sometimes we are aware that E cell only applies to standard condition, and then the change in concentration, pressure, temperature may affect the electrode potential value. So they might affect your prediction, your ultimate prediction. So unless you are given the Nernst equation, if not, you might not be able to give a good prediction. Okay, and remember that the standard cell potential, ultimately we are still talking about a thermodynamic parameter. So whether a reaction is thermodynamically feasible, but we all understand from the topics of kinetics that sometimes thermodynamically feasible, but kinetically it may be difficult to occur. Yeah, so for example, the reaction between copper-2 and hydrogen gas, thermodynamically it can take place, but kinetically it's going to be really slow because the probability of the hydrogen interacting directly with copper-2 is very minimal. Okay, and therefore it has a very high kinetic barrier. Yeah, so if you do not take into consideration kinetic feasibility or the activation barrier, you may just predict that the reaction is thermodynamically feasible, but sometimes that reaction might not occur at appreciable rates. Okay, and then next 3.5, we have this interesting learning objective. We are supposed to apply delta G is equals to minus NFE cell to electrochemical cell to calculate the E naught for combined reaction. Okay, so quite a bit of mathematics here, but I'm just going to, although the mathematics has already been given to you, but I thought I can just run you through. Okay, so first of all, right, you will notice from your data booklets that iron has three half equations. Iron 2 to iron, iron 3 to iron, these are the two values, and then iron 3 to iron 2, which is 0.77 volts. Okay, they are all written out here. You notice that from iron 3 to iron, it's not, I cannot simply just add equation 1 and equation 2 together. You know, when I add the equation, right, when I add both equations together, you notice that iron 2 gets cancelled off. But you notice that if I add these two up, I will not be able to get minus 0.04 volts. Yeah, you might be wondering why is that the case. Yeah, because you cannot just add the equation up directly to evaluate a new E naught. You have to ensure, that means that it can only be solved by a Hess cycle, which is what you learn from energetics. Yeah, so therefore you have to convert them to delta G. Okay, so over here we converted them to delta G. So delta G1 is equals to minus NFE, so 2 electron transferred, 9650 blah blah. I'm going to get 84,920 joules per mole, and then delta G2, and then I'm going to get negative 74,305 joules per mole, and then you know that delta G3 is delta G1 and G2 together. I combine the two, I get about 10,615, and then you know that E naught is actually equals to delta G divided by the number of moles of electron transfer multiplied by Faraday. So I'm going to end up with this value. Yeah, so that means when you want to determine the E naught from the equation, you cannot simply just add the equation out and then add the E naught up and expect a result from there. You have to convert them to the energetics variable, which is delta G, and then solve using Hess cycle. If you're a little bit confused, it's okay. We can look at exercise 3.3. I think that will make it easier. Okay, so first of all, the standard electrode potential and Gibbs free energy of different chlorine species are given below. You see over here, right? We gave you different chlorine containing species. Yeah, remember that from our data booklets. For reaction involving chlorine, we only have chlorine chlorides, as well as chlorine +1 oxidation state in the acidic medium and in the alkaline medium, and these are the values given to us. But we do not have the full suite of values, including chlorine 7, chlorine 5, chlorine 3, chlorine 1. Okay, so because of that, if an exam question requires you to do some evaluation, we have to incorporate some additional data for you. Yeah, so that is the purpose of this question. Okay, so we'll just do it quickly. So first of all, calculate delta G naught for half equation 2. Okay, not half reaction, half equation 2. Okay, so what can we do? We can simply just use delta G. Okay, delta G2. Okay, or rather delta G because yeah, delta G is actually equals delta G naught is actually equals to minus, okay, 10 electrons is being transferred, right? So minus 10 multiplied by 1.47. This is given to us. Okay, and then multiply by 96500, and then over here I'm going to get negative 1420 kilojoules per mole. Okay, so this is the value I end up with. Right. Okay, so the standard electrode potential of converting chloride 5 to chloride is not the summation of 1.47 and 1.36. I think we have already talked about it just now. This is because number of moles of electron transferred must be taken into consideration. Okay, so write a half equation for the conversion of chlorine 5 to chloride or chlorine minus 1. Use our knowledge of Hess cycle for delta G, and then your answer to A show with the aid of a energy cycle, the E naught is 1.45 volts for the conversion of chlorate 5 or chlorine 5 to chloride. Okay, so I think the first thing we might need to do is simply to add up the half equations together. Okay, so I think first of all, we need to write a balanced equation involving ClO3 minus all the way to Cl minus. Okay, so we can do that by simply adding up equations 2 and 3. Okay, so if we add up equations 2 and 3, we will end up with 2ClO3 minus equals plus 12H plus equals plus 12 electrons. Remember the chlorine cancel off. Okay, so we don't have to include chlorine. And then we are going to end up with 2Cl minus equals, okay, plus 6H2O liquids. Okay, so if we were to apply Hess law, okay, so the first thing we need to do, maybe we can write out the equations. Okay, so this is the equation we're going to write out, and then we just need to apply Hess law. So first we convert this to I think we are getting negative 1420, right? Okay, so we are going to end up with chlorine. Okay, chlorine equals plus 2 electrons plus 6H2O. Okay, so this is directly from equation 2. And then chlorine reduced to 2 chloride. Okay, so this is given to be negative 262 kilojoules per mole. Okay, so from here we can easily determine delta G. Okay, so therefore delta G is equals to negative 1420 negative 262 is equals to negative 1682 kilojoules per mole. Okay, then what we can do here is from the delta G calculated, we're going to apply delta G is equals to minus NFE naught. Okay, so delta G is negative 1682 times 10 to the power 3. Remember, we have to convert it to joules per mole equals to minus 12 electrons is being transferred, minus multiplied by 96500 multiplied by E naught. Okay, so in this case, E naught is equals to, we just divide it accordingly, so we are going to get plus 1.45 volts. Okay, please work it out on your own and prove to yourself that number one, you can use the Hess cycle to solve the question, and then number two, you are able to understand that when we try to obtain the E naught from equations we are given, you cannot simply just add them up like the way you do it. Yeah, I mean like the way you do it while writing balanced equations. Yeah, so that is actually a taboo. Okay, yeah. So next, we're going to move on to the next part on the practical application of electrochemical cell. The practical application is in one of your learning objective 12K, where you are supposed to state the possible advantages of developing other types of cells. So for example, the very famous hydrogen-oxygen fuel cell, and improve batteries as in electric vehicle. I think electric vehicle is a big thing for the past 2 to 3 years. I'm sure you have heard of Elon Musk, Tesla, where the main task now is to bring down the cost of the batteries and to improve its efficiency so as to bring down the cost of the electric vehicle. Yeah, electric vehicle used to be a pipe dream, but as the technology of making the batteries improved, the cost will drop. Yeah, and hydrogen oxygen fuel cell has its fair share of advantage and disadvantage. I guess you can read all this on your own, but I'm going to show you a video which I will put the link below so that you can watch the video in your own free time. I'm not going to show you the whole video, but just part of it.
The world grapples to eliminate fossil fuels from our energy diet. Electric cars have seen an incredible boom over the past few years. Last year, over 1 million electric cars were sold around the world. The number of Nissan Leafs, Teslas and other electric vehicles in circulation worldwide is now more than 3 million. And while there are many brands of electric car to choose from, there are only two choices when it comes to powering electric vehicles: fuel cells or batteries. Both produce electricity to drive electric motors, eliminating the pollution and inefficiencies of the fossil fuel-powered internal combustion engine. Both hydrogen and electricity for batteries can be produced from low or zero carbon sources, including renewable energy like solar and wind, and therefore both are being pursued by car manufacturers and researchers as the possible future of electric vehicles. However, a great debate is being waged by supporters of each technology. Elon Musk has called hydrogen fuel cell technology incredibly dumb, claiming they're more of a marketing ploy for automakers than a long-term solution. In contrast, Japan has announced its intention to become the world's first hydrogen society, with the Japanese government and the auto industry working together to introduce 160 hydrogen stations and 40,000 fuel cell vehicles by March 2021. So, which is actually better? At first glance, hydrogen seems like an extremely clever way to power a car. Compressed hydrogen has a specific energy of nearly 40,000 watt-hours per kilogram. Lithium-ion batteries, at best, have a specific energy of just 278 watt-hours per kilogram, but most fall around 167. That's 236 times as much energy per kilogram for hydrogen. And because of its energy density and lightweight nature, compressed hydrogen and fuel cells can power cars for extended ranges without adding much weight, which, as we saw in our last video, is a gigantic roadblock for incorporating the technology into the aviation industry. The designers of electric vehicles are caught in a catch-22 with energy density and range. Each extra kilogram of battery weight to increase range requires extra structural weight, heavier brakes, a higher torque motor, and in turn, more batteries to carry around this extra mass. This weight compounding limits how far a battery-powered vehicle can travel, until new technology can help reduce the weight of the batteries. For hydrogen vehicles, this weight compounding is not an issue. Additionally, a hydrogen fuel cell vehicle can be refueled in under 5 minutes, where a battery-powered electric vehicle like a Tesla Model S takes over 3 hours to fully recharge. When looking at the range and refuel times hydrogen can offer, you can see why some car manufacturers are investing in this technology. On the face of it, hydrogen is a clear winner, but it falls behind when we start considering the end-to-end production process. While both batteries and hydrogen fuel cells are both forms of electricity storage, the costs differ drastically. Fully charging a Tesla Model 3 with a 75 kilowatt-hour battery costs between $10 and $12 depending where you live. With a rated range of 500 kilometers, that's between 2 and 2.4 cents per kilometer, a great price. In a previous video, I visited a petrol station that introduced a hydrogen pump, fed by its own on-site production facility, which used off-peak electricity to produce hydrogen. The hydrogen from this station cost $85 to fill a 5 kilogram tank of the Toyota Mirai on site, which had a range of 480 kilometers. That's 17.7 cents per kilometer, 8 times the price. And here lies the problem. Hydrogen simply requires more energy to produce.
Okay, I'm going to stop here. So if you are interested, you can view the videos on your own. I think it's quite interesting. Okay, yep. So I'm going to jump straight back into the notes. Yep. So I'm not going to waste time talking about all this. You can read on your own. Just going to explain the chemistry of hydrogen oxygen fuel cell. Okay, so if you take a look at this particular diagram, you notice that hydrogen is being introduced in the anodes. Okay, over here it just flow through, so the excess hydrogen will flow through, and then at the cathode, oxygen is being introduced, and then the excess oxygen will depart. Yeah. So at the anode, the hydrogen is being oxidized to give you H2O. Okay. So in this case, I will need an electrolyte, and our electrolyte here is aqueous KOH. Okay. So first of all, hydrogen is being oxidized to H2O, and then oxygen is being reduced to OH minus. In the presence of alkaline medium, water will not be water will probably be produced alongside with OH minus. Yeah. So in the process, the current will flow from the anodes to the cathodes. Yeah. So this is how we can generate electricity to power up, say, our light bulbs. Yeah, but as the earlier video showed you, it was said to be highly expensive and not very efficient. It is largely due to the cost of producing pure hydrogen. Yeah, because if you go through the earlier videos, it was mentioned that hydrogen, the bulk of it exists in water, and as well as the fossil fuels. And in order to abstract out the hydrogen, it's actually more expensive to abstract it out than to just burn the fossil fuels, etc. So I think you can read about it. So until we find a very efficient way to produce hydrogen, if not, cost will always be an issue. Okay, then we'll move on to exercise 4.4. Okay, so this should be exercise 4.4. Just this is a mini typo. Okay, so the Italian catalyst manufacturer Actor proposed using hydrazine as an alternative to hydrogen fuel cell. So the chief benefit of using hydrazine is that it produces more energy than a similar hydrogen fuel cell. Okay, so I have the example over here. So I have hydrazine being introduced, and then the product is nitrogen gas and H2O. Okay, the anion exchange membrane consists of OH minus as the electrolyte. So we are asked to write down the ion electron half equations for the reaction that takes place at each electrode. Okay, so I think first of all, we need to look at the anodes, which involve hydrazine. Okay, you notice that the anode produces N2 and H2O. Okay, so we'll try to write down the balance equation. So N2 H4, I'm going to get N2. Okay, do take note that for this particular reaction, you must balance it on your own. It is not given in the data booklet, so you can go to the data booklet and search. There is no reaction involving hydrazine. Okay, yeah, so you have to write down the redox equation on your own, and you are more than capable to do it because you have done that in JC1. Okay, yeah, so we'll do the oxidation. We'll just calculate the oxidation states. Okay, so the oxidation state of nitrogen here is minus 1. Okay, the oxidation state of nitrogen, not minus 1, it's actually minus 2, and the oxidation state of nitrogen here is 0. So each oxygen is being oxidized from minus 2 to 0. So on the whole, 4 electrons is being given out, and because 4 electrons is being given out, we need to balance the charge. So we balance the charge using OH minus. So left hand side is 0 charge, right hand side minus 4. So I'm going to add 4 OH minus on the left hand side. This equals, okay, and of course I'm going to add in the relevant number of water molecules, so that will be plus 2H2O liquids. Okay, and then this is the reaction that is taking place at the anodes, right? And then the reaction taking place at the cathodes, you can easily go to your data booklets. Just go to the oxygen. You look for the one involving the alkaline medium. Okay, so that's O2 plus 2H2O plus 4 electrons, so that will be O2 plus 4 H2O, so this is gas, liquid, plus 4 electrons. I'm going to get 4 OH minus aqueous. Okay, so I'm going to add the two equations up, and then I'm going to end up with N2H4 liquids plus 4 OH minus aqueous. I'm going to get N2 gas plus 4 H2O liquids. Yeah, that's it. Sorry, plus 2 H2O liquids. Okay, so this 2 H2O liquids. Okay, yep. oops, sorry, there shouldn't be OH minus because it gets cancelled out. Okay, what am I doing here? Okay, so let me just cancel it out. Okay, so I'm going to cancel this out and then cancel, of course. Okay, so this should be oxygen. Okay, yeah, my apologies. Oxygen, yeah. Okay, then next, given that the standard electrode potential for N2, N2H4 is minus 1.16 volts, calculate the cell EMF if the process takes place under standard condition. Okay, so this should be pretty straightforward. Okay, because E cell, okay, is E reduction minus E oxidation. Yeah, so in this case, what is being reduced? Oxygen, water, so that's O2/H2O minus E oxidation. So what is being oxidized? Hydrazine is being oxidized, so N2, sorry, this is N2/N2H4. Okay, so this will be 0.40 minus 1.16. I'm going to get positive 1.56 volts. Okay, and then based on the physical properties of hydrazine suggests an advantage of the hydrazine oxygen fuel cell over the hydrogen oxygen fuel cell. Okay, so hydrazine, of course, is a liquid at room temperature, so it's easier to be handled and stored, whereas hydrogen, again, you need to watch the videos earlier on the truth about hydrogen. It needs to be either compressed or it needs to be cooled down under very cold temperature, let's say negative 200 over degrees Celsius, which is very costly. Okay, yeah, so these are the two major issues with hydrogen, and with hydrazine, it is not a major issue. Okay, then we're going to move on to 4.2 on batteries. Okay, so we have non-rechargeable alkaline batteries, the one you use in your radios, portable radios, toys, flashlights. Okay, the one you can buy from the supermarket. Okay, so you have an insulator, graphite rods, which is the cathodes, and then the MnO2 in potassium paste, and then a zinc anodes with an outer steel casing. Okay, so you have a plus minus. I think you have seen that in your batteries as well. Okay, so what exactly happened here is that the zinc will be oxidized to zinc oxide, because in the alkaline medium you can't get zinc 2+. Okay, that's what happened at the anode, and then at the cathode, manganese dioxide will be reduced to manganese hydroxide. Okay, so in the process, 2OH minus is being given off. So this is the overall equation. Okay. Oh, people forgot to mention that you're not supposed to memorize all these equations. They are just used as an example to show you the different practical application. Yeah. So your job is really not to memorize all this, because if any of these is required, we will give you the data, and then you can apply them accordingly. Okay, then next we have a non-rechargeable silver button battery, the small little button-like battery you use in your watch, cameras, heart pacemakers, okay, or hearing aids. So you have a zinc anodes and then a metal cathodes, and then the interior is made out of the silver 1 paste, okay, which acts and then it's being separated from the zinc electrolytes. Okay, so at the anode, zinc is being oxidized to zinc oxide, similar to the above. Okay, and then for the cathode, silver 1 is being reduced to silver. Okay, so this is the overall equation that is taking place. It's able to generate a cell potential of 1.6 volts. And then for the car batteries, rechargeable lead acid battery used to power the starter motors in a car. Okay, so if you are interested, you can watch this particular video.
12-volt lead-acid car battery. These large and fairly heavy batteries are used in every combustion engine vehicle on the planet. They're an essential part of the vehicle. So what does it do and how does it work? That's what we'll be covering in this video. The 12-volt car battery looks something like this. This is a lead-acid battery. We call it a lead-acid battery because inside the unit are lead plates, which are submerged into an acid. This creates a chemical reaction, which releases energy and provides us with a voltage and current. The battery is therefore storing energy in the form of chemical energy. It does not store electricity. This chemical energy is converted into electrical energy whenever we need it. This battery is also rechargeable. If we supply the battery with electricity, then we can reverse the chemical reaction and recharge the battery. These types of battery provide large amounts of current, especially compared to the typical smaller household alkaline batteries. The typical car battery is found in the engine bay of the car. The battery is first used to start the engine, and it does this by providing electricity to a small electrical motor known as the starter motor. The starter motor engages a small gear onto the flywheel of the engine. It turns this to turn the crankshaft, which starts the combustion engine. The small gear then disengages and the engine runs by itself. The starter motor needs to provide a huge amount of force to be able to turn the flywheel. So the starter motor will draw an extremely large current, possibly hundreds of amps, but this is only for a few seconds. This large current demand is going to reduce the energy storage of the battery, so we will need to top this back up. Connected to the engine is an alternator. The alternator is rotated by the engine, and as it rotates, it generates electricity. This electricity is fed back into the battery to recharge it. While the engine is running, the alternator recharges the battery, but it also provides the electrical power for things such as lighting and the music system. When the demand for electricity in the car exceeds what the alternator can provide, then the battery will provide this additional power, which again drains the battery. If the engine is switched off, the alternator stops rotating and recharging the battery. So the battery will provide the full electrical power to the car until it's dead. At this point, the battery can't provide enough electricity to start the engine, so we will need to jump start the car. Let's have a look at the main parts of a car battery and then we'll understand how it works. First of all, we have the plastic case which holds all the internal components in place. On the top, we have the plastic lid, and there are two terminals, a positive and a negative. By removing the lid, we can see inside. Notice the casing is divided up into 6 separate chambers, each separated by a plastic wall. Each chamber is known as a cell. Each cell generates around 2.1 volts of DC or direct current. Each cell is connected in series. The negative of one cell is connected to the positive of the next cell to give us a total voltage of around 12.6 volts. It's the same as if you connected household alkaline batteries together. The voltages add together to provide a higher total voltage. Each cell in the battery is connected via a plate strap. This is made from lead. These straps are welded together through the plastic wall to form the connection. As we look at the battery from this view, we see the current flows through the battery cells from the positive to the negative, and that's using conventional current theory. But what's actually happening is the electrons are flowing in the opposite direction, from the negative and to the positive. But we'll cover that and you'll see why a little later in this video. Notice there are 2 plate straps in each cell, one positive and one negative. These are called plate straps because each strap is connected to a number of plates, which are sheets of lead. The plates are formed into grid-type structures, which maximizes the surface area. The grids are coated in a paste of lead oxide. The paste is where the chemical reaction occurs, and we'll see that a little later in this video. The paste acts a bit like a sponge and is going to absorb some of the electrolyte liquid, which improves the battery performance. The size of the plate determines how much current a battery can provide, but it doesn't change the voltage. The materials used for the chemical reaction and the number of plates determines the voltage produced by each cell. The grid holds the paste in place to ensure a uniform current distribution across the plate and helps to transport the electrons out of the battery and around the car's electrical circuit. The negative plate is the anode, and this is a plate of pure lead, although some small amounts of additives are added to harden the lead and protect it from corrosion. The positive plate is the cathode, and this is made from lead oxide. The plates are made of dissimilar materials to form the chemical reaction and release the electrons. Now, we don't want the positive and the negative plates to come into direct contact with each other, because this would short circuit the battery. So, instead, we place each positive plate into an envelope separator. This is just a porous material that allows ions to flow through it without the materials coming into direct contact with each other. The positive and the negative plates will sit between each other with a small gap in between each plate. The chamber is then filled with an electrolyte liquid of sulfuric acid and water. Hence the battery is called a lead-acid battery. I want to quickly recap on the fundamentals of electricity so that you understand the next part of how the battery works. Electricity is the flow of electrons in a circuit.
Okay, yeah, so I'm going to stop here. Again, I'm going to provide the link below. If you are interested, you may continue to watch the videos, because it gives you quite a lot of information on how the lead-acid battery works. Of course, the later part of the video is more on physics. Yeah, so recall earlier on that the anodes consist of lead, pure lead with some additive to strengthen it, if you can recall, and then it will be oxidized to lead sulfate, and then the cathode consists of lead 4 oxides, and then it will be reduced to lead sulfate. Okay, so it's actually reduced to lead 2, but the lead 2 will then react with sulfuric acid because it will precipitate out as lead sulfate. Yeah, so the overall cell reaction is sorry. So the overall cell reaction is lead 4 oxide and lead together with sulfuric acid, and in the process I get lead sulfate and H2O. Yeah. Remember from the video that the cell potential we're going to get is 2.1 volts. Yeah. So when the cell is recharged, I'm going to reverse the reaction. Okay, so recharge means the reaction will be reversed to give me back lead 4 oxide and lead. Yeah. Okay, so remember that the forward reaction is spontaneous, but the backward reaction is non-spontaneous. So in order to force out the non-spontaneous reaction, we have to connect it to a external power supply. Okay, so the next one will be a rechargeable lithium-ion battery, which you are familiar with, maybe not with respect to the structure, but with respect to everyday usage. Because nowadays all the mobile phones, laptops, your iPads, all the batteries are lithium polymer batteries. Yeah, okay, yeah, so the structure looks something like that. I'm not going to go into details. Again, if you're interested, you can watch the relevant videos related to it. Okay, and then what exactly happened at the anode is lithium is being oxidized to lithium 1, and then give out an electron, and then for the cathodes, lithium 1 will then be reduced to lithium, but lithium 1 is not the one being reduced, I'm sorry. It is cobalt 4 that is being reduced to cobalt 3. Okay, yeah, so with that, the overall cell potential is 0.34 volts. You'll notice that for the lithium polymer battery, it's able to generate a very large cell potential. Yeah, so the reason being because lithium has one of the most negative reduction potential. Okay, yeah, I think it's given here as well. Advantage of battery is that lithium has the most negative E0, and then it's the lightest metal, and then it can be recharged literally hundreds of times without deterioration. Okay, and then rusting is also an electrochemical process. Okay, so we apply paints to prevent rusting. Yeah, but let's say the paint layer wears off, then what happens is that the iron will then be oxidized to iron 2. Okay, so so on the surface, the water acts as interaction with the surface of the iron. So that will be the cathodic site, where oxygen gas is being reduced to H2O, and then the electrons will be forced to flow from the anodic site to the cathodic site, and then at the anodic site the iron will be oxidized to iron 2, and then it will then be further oxidized by oxygen to give you rust. And the thing about rust is that it's very flaky and it doesn't stick very well, and it wears off eventually if you scrape it off, and that will further expose more iron to other to the moisture and for further oxidation. Yeah, so iron oxide is actually one of the most crucial problem whenever we have iron and steel. Yeah, so in order to prevent corrosion, we tend to paint them, or we can try to apply a sacrificial electrode, but that is something which you have learned from secondary school. Yeah, so if you recall, in the ship, we tend to use magnesium as the sacrificial metal. Okay, so these are the reaction taking place. Oxygen reduced to water, and then iron oxidized to iron 2, which will be further oxidized to iron 3 oxide, which is a form of rust. But rust is more complicated than this. It actually takes place, it actually has many forms. Yeah, so this is not the only forms of rust. And because rust is so complicated, and it has created a lot of problem, and that is why the prevention of rust is of utmost importance for the past few hundred years. Yep. And then that's the end of section 4. In the next series of videos, I think in segment 3 of the videos, we're going to complete the lecture by first beginning with section 5 on electrolytic cell, otherwise known as electrolysis.